Hi, today I wanted to talk about um, declarations, pointers, and function pointers in C. Talk about some of the trickier aspects for beginners. Um, I was also a beginner C programmer once, and I want to say um, some of the concepts are need to be understood thoroughly. And if they're understood thoroughly, C is it's not that hard. But if it's not understood thoroughly, it can be confusing. So here I have a MacBook, but I have a software called VirtualBox where I installed a instance of Linux Mint. So that's a Linux virtual machine, and that's what we have here. And let me just maximize the screen. Okay, great. So now I want to just so I've already done this once in declarations.c. That's my own exploration, but now I will do it from scratch again. I will call it declar and pointer.c. Declarations and pointers.c. And I will just dive right in and show you so right here I have a main function. I'm going to return 0. And in this main function, I want to declare an int int pointers b and c, and int d, something like that. I'll initialize this to 3. I'll initialize this to 5. These are just somewhat arbitrary. And at this point, well, before we go any further, actually, there is more and more I'm seeing nowadays people declare their pointers like so, where it's int pointers int star space x, where in their mind they're thinking x is an instance of an int pointer. But that is actually not how it's meant to be thought of. It should be, instead it should be int space star x, and in this instance star x, so dereferencing x, you get an int. That's how you're supposed to think of it. When you dereference x, you get the type int. And then this is also equivalent to if you put parenthesis right here. The pointer naturally binds to b, and int is sort of separate, if that makes some sense. So you can have int parentheses star x, that's equivalent to int star x. And then if you were to declare multiple pointers, you would do the following, and you would not correct. You would not do this. B. That's not correct. So I encourage, if you're new and you see code that's like this, I encourage you to not do this, and I encourage you to do this. It's the more proper way to think of these types, these pointer types. So now I have 4 types, and I think the best way to reason about pointers is to look at the actual addresses, to look at the addresses of variables. So here I'm going to print out, so pointers are now 48 bits and they're contained in a 64-bit field. So if I want to print out pointers, I better cast them into unsigned long. So now I have my declarations and pointers.c. I can compile it. I want to turn on all warnings. I want to use the C11 standard, which is the latest standard. And I just want to do this. C is used uninitialized in this function. I am an idiot. What I meant to do is look at the reference of all these guys. So now you see that these are the addresses of these four variables, A, B, C, and D. And you see their values are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times 48. They're all 40, actually they are all 47 bits long, which is quite interesting. Interesting. So these four variables, as you guys know, are on what's called the stack. And these addresses are actually not physical addresses in memory, but virtual addresses. And they go from 0 to, I believe, 48 ones. Binary representation with 48 ones. So all Fs here, 12 Fs. And from this example, I can see that the stack, it starts somewhere in the 7FF territory and goes upwards. And one interesting thing is that A is at B00, B is at B08, C is at B10, and D is at B04. Is that... Oh, I see. So the compiler actually put the two integers A and D next to each other because they're of a different size. They're 4 bytes long, as you can tell by the fact that it only skips 4 bytes here, and then it skips another 4 bytes from D to B. But then B and C are the two pointers are a little bigger. So on the stack, they're aligned such that the compiler aligns them in such a way they're not in the same alignment as I've declared them. Is it because I've initialized them with a value? I wonder. I doubt it. I doubt it's because I've initialized them with a value. No. It has nothing. It's not because I've initialized them with a value, and we see the same behavior. So one thing to note is that between compilations, these addresses change a little bit. So the actual mechanism of making these virtual addresses is actually quite complex. I don't even know exactly what happens, but the things to note is that the addresses are very high, around 7FF area, and that the relative alignment to each other is such that they're all sort of next to each other. Although the compiler did make the change where they put the two ints next to each other and then followed by the two pointers. And ints are 4 bytes, as you can tell. This is 4 bytes off from here. This and this is 4 bytes off. That's the room for the two ints. This and this, they're 8 bytes off. From 88 to 90 is actually 8 bytes because we're in hexadecimal. And pointers are 8 bytes. Although pointers only use 48 of the, pointers use 6 of the 8 bytes, 48 bits. Anyway, now we can do something interesting. We can say a unsigned long. Let's call it f. Let's have it be equal to unsigned long, the reference of d. And now I'm going to printf %lx f. So f is now the address of d casted as an unsigned long. You see that the address of d casted as an unsigned long, it can be printed just like anything else. However, now what we're going to do is we're going to print an integer in decimal form of, we're going to cast f as an int pointer. So f is now just a number. F is just a number. But we're going to cast it as a pointer, as an address, and dereference it. And what I expect is that, so f is a number that contains the address of d. And if I cast it into an int pointer and dereference it, I will get the value of d, which is 5. So let's see if that actually happens. You see, it's 5 as we expect. Now, to do something a little bit more interesting, just like variables have types, functions have types, and we can create pointers of functions as well. So I'm just going to create a function, a very simple function. This. And now I am going to, I'm going to use a print line here. I'm going to print out the address of addInts. So this function will just be compiled into a list of machine instructions, and they will be put into memory. And there is an address pointing at the first instruction of the function, just like a variable. So I will have to cast this as an unsigned long. So you see that this is the address of my function adds. Now for something kind of gnarly. So functions get put into the lower addresses of the virtual address space, and the stack is in the higher end. This is sort of a convention. This is sort of how Unix works, or Linux. I wonder if it starts from 400000. But anyway, if I remove the executable and recompile this and rerun it, so I've noticed that these addresses change, but the address of this function doesn't. It sort of stays the same. So I'm going to show an even more explicit example. So notice this number is 4005D6. In fact, I will copy it. Because I'm using a virtual machine, copying is not as simple as using an actual Linux terminal. So now what I'm going to do is I am going to print an integer in decimal form. That is, I am going to paste. So this is a hexadecimal number, and I'm going to cast this into a pointer that takes 2 ints and return an int. So I'm going to cast this into a pointer to a function that takes 2 ints and return an int. And then I'm going to dereference this. Sorry. This is a function. This is a pointer to a function that takes 2 ints and return an int. I'm now going to pointer to a function. I'm going to dereference this to get the actual function. And now I am going to call this function with A and D. Whew, let's see if this works. Wow. So so basically I took this address stays the same, and I just sort of just noticed this fact, and I am just hard coding this address and casting it as a pointer, and then now using it as a function. So this is very interesting. This sort of lets you visualize what's actually happening between addresses and the contents of addresses. Basically, addresses are just numbers. Contents of addresses can be numbers or machine code. It can be anything. And if we know the address, we can cast the contents to what we know those contents to be, and then use them in our C program, if that makes sense. I don't know. Sometimes I worry that I'm speaking in a way that's not making any sense. Let's see. So this can be made a little more explicit if I use a type def. I will type def this type int pointer int int. I will type def this as a function pointer. And then here, when I'm casting, I can just say func pointer. And I expect the same result. And indeed, we have that. And even more interesting is, let's see, we can have let's see. I will declare this type and then declare func pointer as this, and I will declare my function here, and now I can move, since I've declared it, I can move my definition elsewhere. Like this. Now it should behave just as before. Whoa! Whoa! What in the world? Let's see. Let's see what happened here. Let's see what happened here. It's sort of executing my code, but in a loop somehow. Ah, I see what happened. I see what happened. Because I think because I moved the function, the position of this function, or something with adding these types, the address of the function changed to 4006BB. I mean, it's still relative in the same area, but now it's in a different area. So now, when I cast this as a function pointer and make this call, God knows what's actually here. It's probably reference. It's probably somewhere in. It's probably going through main again somehow, but then it must be hitting a jump instruction and then repeating itself. That is interesting. So now you can see how things can get tricky and dangerous. Messing around like this. Oh. There's no undo. Apologies about this. So I want to 4006BB. I want to insert the number 4006BB. Let me try this again. There. We're back to normal. And let's see. We can even move this. We can even move this inside our main function. And we can also reuse the same type. So now you see that the function type is sort of just like any other type. Sort of has a lot of similarities. So now these look like variable declarations instead of function declarations. So I can do something like this, and let me print this out. I wonder if the address of addInts, the function, stayed the same. I have a feeling it might change. And this manipulation of casting numbers into actual hard-coded numbers into pointers is not advised. It's actually it can lead to there's no, you can't count on anything being at a certain address. It's OS dependent, or it's if you take this code into and put it on try to run it on a machine, it would guarantee not to work. Basically, guaranteed not to work. And let me first get the address of sub. So, illegal instruction. Interesting. So the address of both have now changed. 60 and 64. 60, 64. 660. C0. '64. X 40064. Now let me try. Segmentation fault. Interesting, the address has changed again. 6E2, 6F6, E2 and F6, E2 and F6. I think adding this instruction altered the address of both of these functions because the size of main changed. I think, wow, something like that. I actually don't know exactly what's going on, but that's about what's going on. E2 and F6. E2, F6. There we go. We see 5 minus 3. 3 minus 5 rather, -2. Yep. Anyway. I know that I went through a lot of stuff and my presentation is not that great, but hopefully you can get something out of this. All right, thank you.